Today, I will be presenting the first in a three-part series of webinars addressing aerospace fuel system modeling with Flowmaster. I'm going to start today's presentation with a brief overview of the benefits of using one-dimensional CFD software in the engineering process. We will then look at a one-dimensional fuel system model for a typical two-engine passenger aircraft. After looking at the model in detail, we will perform a case study focusing on ground refueling. We'll start with a simple steady-state pressure and flow distribution analysis, and then move on to addressing issues of balanced flow. Then we'll do a fast transient analysis of a potential water hammer or transient surge event. Lastly, we'll wrap things up and I'll talk a little bit about upcoming topics in this series. Risk is always a concern for companies, and usually, as a project progresses, the risks associated with a project tend to decrease. One of the main driving factors behind this is the increase in information that naturally happens as a project matures. By gaining knowledge very early in the process, designers and engineers can lower that risk even sooner. This is where upfront simulation can add significant value to the process. By allowing engineers and designers to investigate a growing number of prototypes virtually before any physical models are constructed, investment in upfront CFD can have significant value by lowering physical testing efforts later in the design. Because physical testing is time-consuming and expensive, virtual prototyping allows more variants to be examined in a shorter amount of time. Flowmaster fits into this idea because it is a one-dimensional computational fluid dynamics simulation tool that allows engineers to simulate complex thermofluid problems at a system level so that they can understand aspects of the design such as pressure, temperature, and flow rates throughout the design. Access to performance data early in the design process is always a challenge, but Flowmaster supplies built-in data from DS Miller out of the box to give you a baseline to work from. You can investigate both steady-state and transient behavior in your systems, which we will look at examples of both today. You have the ability to simulate different types of fluids, including liquids, gases, refrigerants, and steam. There are also a host of specialty solvers for both complex phenomena like swirl and priming, or for making potentially repetitive tasks simple, such as performing a flow balancing analysis. Flowmaster has been helping its users meet these requirements for over 25 years across many industries throughout the world, including our focus today, the aerospace industry. With the introduction done, let's get to the core of today's presentation, the design and analysis of an aircraft fuel system using Flowmaster. Here is the schematic representation of the simplified passenger aircraft fuel system that we are going to build. The three large blue sections represent the wing and the center fuel tanks. The white boxes represent pumps, and the fuel feed and transfer plumbing is represented in green. Refueling lines are represented in dark blue, and shutoff valves are depicted throughout the model as the circular symbols indicating normally open or normally closed. Here is a Flowmaster system model drawn directly on top of the schematic image. We've added source components for our boundary conditions, and extra loss components for items like filters and couplings. You'll also notice that the tanks do not take up the whole area outlined in light blue, but instead are single discrete components. The thin link lines represent a direct connection between adjacent components. They're not pipes. Nodes sit in the middle of the links and serve as convenient points to enter elevation data and interrogate flow results of temperature and total pressure. Let's zoom in on one side of the aircraft model to take a better look at what these components are and how they function. Looking in close detail on the left side, which is a mirror of the right, you can see how we've built our model out of individual components that stand in for their physical counterparts. The engine is modeled as a flow boundary condition attached to a simple shutoff valve. The cross-feed piping that connects the left to the center to the right-hand side of the aircraft is modeled as a series of basic pipe components. Two redundant mechanical transfer pumps submerged in the tanks are modeled with the rotodynamic pump component. A check valve is added to prevent reverse flow. The tank is modeled here using a 3-armed tank component that allows for 2 outlets and 1 inlet, but the 3 connections will act independently as inputs or outputs based on the flow conditions in the model. This tank component can model heat transfer effects and has simple compressible gas model for the ullage space. In the third part of this webinar series, we will replace this component with our advanced tank model to look into more detailed venting and inerting scenarios. For refueling and transfer between tanks, a shutoff valve, filter, and size transition are modeled. The valve is a simple ball valve component that applies the built-in data from DS Miller's internal flow systems in the form of a loss coefficient versus valve position function. This filter is modeled as a generic discrete loss that can take a non-dimensional loss coefficient or a function of pressure drop versus flow rate as an input. You can also see piping to model the transfer and refuel gallery. And lastly, the refueling port modeled as a flow source component along with another discrete loss to model the pressure drop across the refuel coupling and a filter screen. In the center of the drawing, we can see more detail of the components that we used in the model. Crossfeed piping and isolation valves are modeled with more elastic pipe and ball valve components. Center tank transfer pumps that feed directly into the crossfeed line or the refuel gallery depending on isolation valve position. Another 3-armed tank component. And piping to transfer fuel from the center tank into the refuel gallery to replenish the wing tanks during flight as opposed to directly feeding the engines. A similar filter and valve assembly makes up the refueling input to the center tank. And lastly, an APU is modeled, along with a shutoff valve at the aft of the aircraft. Like the engines in this model, the APU is simulated with a simple flow boundary condition. With the initial design of our model in place, let's try applying it to some real-world scenarios to help further refine the design and sizing of our system. For this first webinar in the series, we're going to focus on the single scenario of ground refueling. We can use the same model, we'll just configure it for this particular case and focus on the tanks, inlet valves, and the refueling gallery piping. The goal of our study will be to optimize line sizes and flow restrictions in the system to balance the flow as much as possible for single-sided refueling. Once that's complete, we can identify a steady-state pressure at the coupling that provides our desired flow rate. After that study is complete, we will investigate if a sudden valve closure at one of the tanks introduces surge or possibly even cavitation into the system. If it does, we can investigate methods to mitigate that surge. For our initial analysis, we're going to set the left side refueling flow rate boundary condition to a volumetric flow rate of 500 gallons per minute. We're also going to fill all 3 empty tanks simultaneously and try to understand the pressure and flow implications of simultaneous filling. Since our focus is on the refueling portion of the model, we'll set the engine and APU flow boundary conditions to 0 flow, close off the feed valves, and stop the pumps to isolate that portion of the system. After running a steady-state simulation on our model, we can see some initial flow rate results. Here you can see the boundary conditions are showing the values we set, which should not come as a surprise. The interesting results are the flow split going into the left, the center, and the rightmost tank. The left tank, being so close to the refueling port, receives significantly more flow than the rightmost tank, which could lead to a dangerous imbalance if left unchecked. Looking at results of absolute pressure in the system, we can see why that imbalance in flow is occurring. The large pressure drop across the refueling line leads to a difference in flow and is problematic. These results also show the back pressure at the refueling port of 33.5 psi that gives us our desired 500 gallon per minute fill rate. This will be important to know for a later analysis. Switching to results of pressure difference, we can take note of where the major losses occur in our system. The refuel coupling and strainer is very restrictive. The refuel line on the left-hand side is carrying more than twice the amount of fuel as the right-hand side, leading to more pressure loss between the left and center tanks. Lastly, the fuel filters at the inlets to each tank have a significant pressure loss, but due to the unbalanced flow, the values of that loss vary from left to right. Now that we have our initial steady-state results highlighting a potential issue of flow imbalance with single-sided refueling, let's look at how we can use Flowmaster to perform what-if scenarios to determine a potential solution. In today's presentation, we'll start by looking at a possible change to the flow restriction at the tank entrance. Here you can see the data entry form for the loss component, where we'll try an increased value of loss coefficient. This is a non-dimensional description of pressure difference as a function of flow rate. This could simulate anything from using a more restrictive filter to using some balancing component like a venturi or an orifice. At this point, we don't care what we use to restrict flow, we only want to see what balancing effect it might have. After increasing the loss coefficient of the component from 10 to 50, our pressure difference results climb significantly, but are proportionally closer together. With a fixed volumetric flow rate boundary condition coming into the model, this may give us the more balanced flow we're looking for. Here are the results of volumetric flow rate, and indeed, the flow to each of the three tanks is much more in balance. However, due to the increased amount of loss, we've raised the required pressure to achieve our 500 gallon per minute flow rate significantly, from about 30 psi to over 50. After increasing the restriction at the entrance to the tank, we see that the flow is more balanced, but is still not the same from left to right. This method also requires a higher input pressure. Because this is only simulation, we can then return to Flowmaster to explore a new option relatively painlessly. We can try a series of simulations to vary the refueling pipe size, which will affect pressure drop along the length of the line. We can then select the best compromise between pressure loss and size, which affects both packaging and the weight of our aircraft. To perform the analysis, we can make use of Flowmaster's parametric capability and assign a variable in all of our pipe components to correspond to our refueling gallery diameter. The Experiments tab in Flowmaster allows us to set one value that instantly updates any component in our model that contains that variable. From this tab, we can also manage an experimental parametric study. The parametric study tool gives us a lot of flexibility to design our experiment. We could manually enter data for each run for every variable. We could also run an automatic study, letting Flowmaster choose values based on our criteria and changing one variable at a time in order to run a truly valid experiment. Lastly, we could apply a Monte Carlo method and run a statistical analysis, which would be relevant if we wanted to understand the impact of an unknown variable, such as manufacturing tolerance. With the automatic method, we have the option to select a start value, end value, and either a number of values or a fixed increment size, like the half-inch diameter increase we're going to use. Lastly, a total number of values is required. The way this works is that you simply pick 3 of the items and Flowmaster will determine the remaining one for you. Once you've defined your study, you can see the experimental batch analysis that Flowmaster will run. And after running, you can see the results. These results are exportable to both XML or Microsoft Excel and can even be used to create a functional mockup, which is an embedded lookup table of results for use in a different analysis tool like MATLAB Simulink. As is clear from the results, as pipe size increases, the flow rates trend toward each other as the pressure drop across each pipe is reduced. Here we can identify a point of diminishing returns at a 4.5-inch pipe size. Based on our packaging requirements, this size may not work, but it seems to deliver decent performance for our needs. With an initial flow balance done and our pipe sizes and filters optimized to deliver our desired flow rate and back pressure that meet our needs, we can move on to dynamic or transient simulation. We can use transient to look at many things like time to refuel or transfer between one tank and another, but here we will apply it to the serious issue of valve closure-induced surge. Pressure surge, pressure transients, or water hammer are all names for the propagation of pressure waves that move throughout a piping system when the velocity of the fluid changes rapidly. This can be caused by valves that close quickly, control or regulating valves that hunt for their desired set point, pump speed changes, or even pump resonance within a system. The amplitude of the pressure wave is described by the Joukowsky equation, where the pressure is proportional to the wave speed of the fluid-pipe combination and the rate of change of velocity. The wave speed is a factor of material properties of the fluid, of the pipe, and also the size of the pipe and how it's supported. In Flowmaster, we solve the propagation of the pressure wave by subdividing the pipe into many segments and using the method of characteristics approach to solve the one-dimensional propagation of pressure along the pipe. One example of where we might observe surge in our system is with a sudden valve closure of a tank inlet while refueling is underway. In our example, we will fill from the left-hand side and close the right tank valve suddenly. We want to look at the magnitude of any resulting pressure wave, any attenuation we see from other elements in the system like open tanks and pipe friction, and also if any resulting surge is large enough to cause the system to cavitate. To set up our simulation, we replace our 500 gallon per minute flow boundary with a pressure boundary at our identified input pressure of 29 psi. We will also close the left and center tanks to avoid any potential attenuation of the pressure wave for this initial study. Lastly, a tabular controller is added to the right tank valve, which will allow us to set a closure time and linear rate to apply to the simulation. For the initial study, we'll use 1/10 of a second closure time. After running our transient analysis, you can see the pressure surge is dramatic and irregular. The pressure spikes up to 105 psi and falls all the way to the vapor pressure of jet A, causing cavitation. If we add the Flowmaster result for cavity volume, you can see that everywhere the pressure goes to the vapor pressure, we're building a vapor cavity in our fluid. This cavity subsequently collapses, creating a secondary wave. The complex interaction between the liquid and the gas phases is what causes the irregular appearance of the pressure spikes. Once cavitation stops, the wave resumes a much more regular shape. The last example was a worst-case scenario. All of the flow was going to one tank, which was furthest away. All of the other tanks were closed, and the valve closure was fairly rapid. Let's run a series of analyses trying a variety of methods to reduce surge and cavitation. We'll leave the pressure boundary condition as is to maintain the same 500 gallon per minute initial flow rate. We will vary the closure time between a slower time of 1/4 of a second all the way to a 1 second closure time. Lastly, we'll repeat the experiment with the valves to the left and center tank open to see if they have an attenuating effect. Here is a plot of pressure versus time for 3 valve closure timings: 1 second, 1/2 a second, and 1/4 of a second. The 1/4 second closure still cavitates significantly with a maximum pressure spike of just under 100 psi. The 1/2 second closure approaches the limit of cavitation and has a maximum value of 60 psi. Lastly, the 1 second closure avoids cavitation completely and only sees a maximum of 45 psi. Clearly, closing the valve more slowly can make a good resolution to our issue. We performed one more study with the valves open and returned to the worst-case 1/10 of a second closure. Here you can see how dramatically different the wave is. The maximum pressure is reduced from over 100 psi to less than 70 and does not cavitate at all. Additionally, the wave is completely dampened after just a few periods. This is due to the movement of mass in the fuel tanks. One interesting result is to overlay the inlet pressure of the center and left-hand tanks and zoom in on the pressure spike. Here you can see how much the wave attenuates the further you move from the closing valve. You can also see the propagation delay imposed by the wave speed of the system. This presentation is the first in a series of topics surrounding the modeling of a typical aerospace fuel system. In this presentation, we introduced the model and performed a few basic but important initial flow studies. These studies solved real-world issues such as identifying an optimum pipe size for our refueling line and selecting flow restrictors to balance flow. We were also able to determine the system pressure required to reach our desired design flow rate. Lastly, we turned to transient analysis to understand the effect of valve closure timing on pressure wave propagation. In the next presentations, we will build on our model and add complexity and detail, first by adding dynamic controls. These controls will allow us to run more complex transient analyses and help design our control systems. These systems will be used to actively schedule flow during refueling so that we can fill the tanks we want, when we want, to the level that we want. We can also model real-world scenarios like inter-tank fuel transfer and full mission profiles to get a grasp of weight, balance, and stability, and range concerns. In the third presentation, we will look in detail at the tank component, adding an advanced tank, which will allow us to study the interaction of the gas in the ullage space with the fuel. We can then perform venting analysis during climb and descent, and also inerting analysis.